Welcome to the demonstration of our compiler. Let's begin with part 1, which is project 1. So I've already set up a file which will show all these kinds of operations that are needed for project 1. Here, as a side note, I've also disabled constant propagation here by declaring a pointer to A, just to show you more in detail what's happening in LLVM. So let's compile the file. Now let's see the output. We can see all these kinds of instructions here. And we can also see that constant folding is happening here for those first three things that are printed. Because they are constant, so it must be constantly folded, and this is also what happens here if you look at the first three things that are printed in LLVM itself, and other things are not constantly printed, but that's because constant propagation is turned off right now. Now let's actually run the thing that we compiled. Okay, so this is the output, right? And now let's actually see what GCC, the reference compiler, gives us. Let's run it, and let's compare now. So this is basically the same, right? Just to show the correctness of the thing. Now let's see the abstract syntax tree. So for the first three things that are actually printed, we can see that they're already constant because of the constant folding pass, the optimization pass, which happened, and as a result, the three things that were printed are reduced to constant. Of course, the other things no, because constant propagation is turned off, like I said. And what else? Yeah, and that's for project 1 basically. So now let's do project 2. So I already have a file set up for that. Yeah, so let's run it, let's compile it. So we actually see two warnings here. We're warning on line 6 because we are implicitly demoting b, which is a float, and then assigning it to an integer. So b is used in expression and assigning it to an integer, so we're losing information for this float. And also we are assigning a pointer p to an integer, but it's actually a constant integer, and we did not put the const qualifier here, so we're getting also a warning. If I did put it, then we will get only one warning for the implicit demotion. So this is what is happening. Here on line 7 there is an explicit cast, and that's why there is no warning. But if I removed it, then we'll get two warnings, and because we're not doing an explicit cast anymore. And as you can see, this demonstrates also decrements and increments, both for suffix and prefix. There's also like comparisons for pointers and pointer arithmetic with arrays, but let's try to compile it now. So this is the result our compiler gives us. Now let's try to run it in GCC. So as you can see, that the output is basically the same, and the only thing that differs is the pointer address, but it's obvious that it will always differ. So yeah, and what else do we have to show? Oh yeah, let's see the constant propagation. So as you can see, there's a declaration of integer d. Now let's see in the tree how it looks. So if we look at the declaration of d, we are actually seeing already the result of the entire expression, this expression, because it's all constantly propagated. So yeah, syntax error. So let's see. I will just try to write some gibberish here, and as you can see, there's a syntax error printed on the line, correct line. Use of undeclared variable. So if I try to print something here, something that's not declared, there will be an error. Redeclaration. So let's try to redeclare it, and then let's try to redefine it, and there will be redeclaration simple d. But if there is a definition, this will be a redefinition instead of redeclaration. So yeah. Now operations or assignments of incompatible types. So let's see here for incompatible types. This should print error because the pointer types are not compatible. So invalid operands to equals yeah. So that's basically correct. Let's maybe try another one. Which can we try out? Let's try this one. So yeah, wrong types: float, pointer, and integer pointer. Also works. We'll try to be really quick here to get it under or equal to 10 minutes. The video. Okay, assignment of an R value. So let's try to assign 1 to 10. L value required as left operand of assignment. Assignment to const variables. Let's try to declare const integer a 10, and then let's try to assign it something else. Assignment of read-only variable. Okay. Simple table. Let's visualize the simple table now. Let's go back to the previous file. Let's compile it, and let's see how the simple table looks like now. Oh, declaration of the redefinition. Okay, it's here. Okay, now let's check the simple table. Okay, nice. So as we can see, this is the global scope, and main is defined here, function main. And then if you go to the function main, we will get different symbols and their definitions and things like that. So for project 3, I have a file set up here. Let's compile it. And let's see the LLVM output. So as we can see, A, B were declared as integers, and C was declared as a float here, as expected, since they are all type defs here. Also, a comment here, this is A, is also as a comment in LLVM, and then we also have the source code line, the original line. For B we also have a block comment, which you can see here as well for B, and then you can see the source code line, and same for returning 0, and then also the original source code line. And yeah, let's see the visualization maybe. So for project 4 I already have a file set up here with enumerations, all kinds of loops, if and else statements, and also a switch statement. So let's run it. Let's compile it first. Now let's run it. Okay, so enter the number of rows, and what it will actually print is like a pyramid. So let's maybe put in 5. Enter a number between 0 and 10, so it will check if it's between 0 and 10. If I do, for example, -1, then it will say it's a wrong number. And now I will loop from 0 to, and let's, for example, I don't put in 40, something like that. Then it will actually loop from 0 to 40 and print all the numbers. And then enter some integer. This is a switch case where it will check if it's a 0, 1, or 2, and otherwise print must be something else. So I will print maybe 2. It's 2, and let's do that again, but with different inputs. So 7 will print more rows, not a number between 0 and 10. If I put in a correct one, then to say great, your number is 10. I will loop from 0 to 0. Then to just print some 0, enter some integer, and if I do something else than 0, 1, or 2, then it will say must be something else. And now let's test it actually in GCC. Let's run it now. Enter number of rows, 7, so it does the same thing. Enter number between 0 and 10, does the same thing. And yeah. Now let's see the visualization. So this is how the symbol table looks like. So these symbol tables are for like loops and all kinds of stuff, and there are many loops where nothing is fine, so it makes sense. Let's actually maybe see the abstract syntax tree as well. Yeah, it's really big, so maybe I'm not going to show it. And just to show that scoping also works, I will run this test, which should print 10, 20, 30, and 40. So let's run it. 10, 20, 30, and 40. Let's run it in GCC. Oh, the comment should not be there. Okay, let's run it now. Okay, it does the same thing. Okay, now for project 5, I set up this piece of code, which does a forward declaration of f, then includes this file, does a define 0, and then uses it here in this f function, and yeah, it returns a plus. So basically, this is our recursive function, and it stops when a or b are lesser than 0. It returns a plus b, and just to show you that this code is actually not generated in LLVM, I put it here. So just to show you that after jump statements, there is no code generated. Same for here. So after a break, I want to show you that this is actually not printed. And yeah, let's try it out. So let's compile it first. And now let's run it. So enter some integer, 5, enter some float 5. Result is 10. So the function is done. And actually, as you can see, after break was not printed. But if I remove the break, then it should print itself, I think, once or twice. Let's try again. Oh, it actually printed itself four times. Oh yeah, because yeah, it makes sense. So yeah. And just to show you that if I forward declare f with a different types of two floats, for example, instead of an integer and a float, then it will actually print an error, semantic error, conflicting types for function f. So it actually does check the signature of the function. And also, if I would put in to the function like too many arguments or too few, then it will also actually print an error. So too many arguments for function f, and if I put into only one when actually two are needed, then too few arguments to function f. So this is also checked. Oh yeah, and if I would, for example, not actually declare the function, but just, I mean, if I would actually not define the function, then it would say a function I've declared but never defined. And And actually, if I would also include the function after main, then it will also work, because it got linked, right? So yeah, it works. So it doesn't matter if I put it after main, because of the forward declaration, right? But if I wouldn't put forward declaration, then it should not work. Yeah, undeclared function f. So, oh yeah, and I also forgot to show you the warning. So, just to show you the consistency, that the consistency of the return type is being checked, we can see in included line 14. So right here that there's an implicit demotion from const float to int, and that is because a plus b is returned, but the return type is integer, but we are actually using a float in the return type. So there's a possible loss of information, and that is actually being printed out and set to the user. And if I would, for example, like try to return a pointer or something, then there should be an error with incompatible types. Yeah, invalid operands too. Yeah, so basically the return type is being checked, and you cannot return a pointer when the return type is of the function is integer. So yeah. And also to show you that functions cannot be redefined, let's try to redefine function f. So I'll just do like a return 0, something like that, and let's check what happens. So yeah, redefinition of function f as expected. So now project 6, arrays. So I've set up a piece of code over here where, okay, let's compile it first. So now we can see we got 3 warnings. So the first warning is implicit demotion from float pointer to integer pointer. So on line 7, that is because we have a float here as an element of the array, but we declared an array of integers, so there's a possible loss of information. Now in this multi-dimensional array definition, we can see that it's made of 2 arrays of length 2. So we have an array of length 2, but then we have an array of length 3. So excess elements in scalar initializer 2 is smaller than 3. Makes sense. And now we have on line 9 implicit demotion from const float to integer, because we are assigning the first element of the first array to a float, and because it's an array of integers, it's possible to lose information. And to show you that there's also you can also pass the strings as char pointers. Let's compile it then and to show you that. So we passed the string as char pointer here, and we printed it, and it works. And we've also like modified the first character of it, and yeah, it works. Let's maybe compile in GCC to see if the output is the same, right? And yes, it's the same. Also, if I don't include here stdio, then there will be an error that it is not included, but yeah, undefined reference to printf studio stdio is not included. So project 7, let's see. So I have a file here set up already, which is enumerations in the struct, as well as pointers to the struct in the struct itself, so as a member of the struct. And what we are actually doing is some stuff basically on the members of the struct. So if we compile it, we will have a semantic warning, and that is on line 11, and that's because we are accessing the 5th element of an array of the struct, and because it's an array of integers, but we are assigning an element, a float to it, to an element of the array, then we'll get a warning that it's a possible loss of information. So there is semantic type checking involved in the struct members. And also if I would if I, for example, declare instead of struct union, then it would also give an error, since it's actually a struct. So instance of union node does not match previous declaration struct node, so it also checks for that. And if I would, for example, access like a non-existent member of a struct, then it will also give an error. So member something of other node struct does not exist. And this is the LLVM code of that file. So it basically uses for LLVM the built-in struct feature in the LLVM Lite. And this is the symbol table, and this is the abstract syntax tree. So now for the optional of project 2, const casting. So I've prepared the file, which is the example file from the project 2 document. So let's compile it. So we received a warning, and that is on line 5, because we are discarding the const qualifier. Makes sense. Now let's run it. And it's 3.1492 as expected, since we are actually disabling constant propagation. If we see the pointer being used, if we look in the tree, it's actually yeah, it's basically how it should be. And if we would remove this pointer, yeah, if we would remove this pointer, then let's run it. Then we will see that actually it's the constant propagation does happen in that case. So 0.789, and yeah, So const casting, so constant propagation keeps const casting in mind. So another optional we have implemented is else if statements. So let's try this piece of code out. Let's compile it and let's run it. So now we have to put in some input. So let's put in maybe 30, and we can see it's equals to 30 because we put in 30. Let's maybe put in a different input like 15. We have something else. Let's maybe try out 10. Then we have equals to 10. So it works. There's also control flow graph visualization here as well as here. This type of control graph is of course unconventional because this is normally how it looks like. But there's also this type of visualization, which just shows like this is basically like an abstract syntax tree version of a control flow graph where you see different nodes going to different basic blocks and stuff like that. And this is the conventional control flow graph. Another option we have implemented is include guards, which if we try it out, if we try to include this file twice, so because we have include guards, there will be no error actually. And let's try this function out as well. So it compiles normally, right? And just simply run it. But let's say we remove this define here, then it will be included twice, and we will have our redefinition basically. We also have like semantic check for end ifs. So if I have if not define included, and there's no end if, then we will get a pre-processing error unterminated if. And if we don't have any include guards at all, then there's also a redefinition. So actually, the way we implemented the pre-processing is by making a new grammar. And the reason why we did this is to avoid cases like this. So if we made a block comment and then we did a define, then if we, instead of making a grammar, if we checked line by line, then we will check line by line, and then we will see it's a define, but actually it's inside a block comment. So instead of just making an entirely new lexer to avoid that, we just made a new grammar for it. It's the same for edge cases, like for example, printing, like defining something like defining something, and then printing a string with something in it. And yeah, if we would just check for instances of something in the entire source code, then the program would not be correct because we would replace this string with 5. But we are actually avoiding that by making an entirely new grammar for pre-processing. Another optional for project 5 is not generating code for conditionals that are never true, as well as not generating code for unused variables. So let's say I have here like a piece of code where I just declare A, which is never used, but B, which is used, and C, which just checks if B is not equal to 20, because we can deduce at compile time that B is always 20 basically after this assignment. Then we know that this condition is never true. So if we compile it, we'll actually see that the code is never actually generated for this printf in this conditional. There's only one basic block because this if statement is never true. And we'll also see that there's a warning for that. So at line 12, so after the entire conditional, we will see conditional is never true. So this entire thing is never true. So yeah, we have also a warning for that. And we also have like because A is never used, so A is never generated here. So what we also implemented for project 7 are structs that would contain other structs. So for example, here we have a struct person, which has a name and an age, and we have also a struct isFriend, which is like a relation where there's person 1, person 2. So so then we make like two persons, person Joe and person David, and then we make them friends, and then we print their names through the friends struct. So let's compile it, and let's run it now. So as you can see, it turns out Joe is friends with David. Now let's see what GCC gives us now, and it gives us the same thing. So yeah, and we also have unions for project 7. So let's take this piece of code as an example. Let's compile it now. And now let's see the LLVM output. So what it does in LLVM is it actually picks the member with the largest size. So in this case, it's the pointer name. So this is if we see in the LLVM the struct person, it only has the pointer to the characters. And if we make object access, so if we do something like that, then we actually do bitcasts instead of get element pointer. So now let's see the difference actually between the union and the struct. And now let's compile it, and we will see the difference now. So as you can see now, we actually have, if it is a struct, we actually have both the car pointer and the age, but in the union we have only one. And we have also get element pointer instead of bitcasts if we use the struct. And if we actually run it with the unions, then we get 20, and if we run it in GCC, then we also get 20. So another thing we did, which I don't know if it counts as an optional, but we have multiple versions of visualization. So, for example, this piece of code. So let's compile it. and we will see that we have like a visualization of this control flow graph, but also this kind of visualization for control flow graph. So this is more like an abstract syntax tree style, and this is like a conventional control flow graph style. We have, of course, the abstract syntax tree visualization, and we have the visualization of the concrete syntax tree for syntactic analysis, and of course we have the symbol table, which is nothing new, but yeah. We've also implemented. I don't know if it counts also as like an optional, but we have also like more warnings than we normally should have, but not by a lot normally. But what we do have is like a detailed warning message. So it not only shows you the collect line and column, which is nothing new. It's not really optional, but it also shows you the stages in which the compiler failed to compile or gave the warning. So let's say I try to include some non-existent file. So then it will give a pre-processing error instead of semantic error. But let's say I declare A and then I do it something plus 2, then it gives us a semantic error. And if I just do some gibberish, then we will get a syntax error. So it gives us a different. It gives us the stage in which the compiler failed, and we also have like semantic warning. So if I declare a const integer, then and then a pointer to that integer, then we discard the const qualifier, so we get a semantic warning. We get a semantic warning here. So yeah.